Hello, my name is Matt Turk. I'm going to wear this microphone because we are actually going to be recording all of the talks that we can and then putting them up online. Yeah, how's that? Okay. My name is Matt Turk, and I am one of the core developers of YT, and I just wanted to give a very brief, sort of introduction to what the workshop is going to be structured like and what you might be able to expect from it. So first off, welcome, and thank you very much to the Flash Center for their hospitality, and thank you very much to Professor Lamb for that wonderful introduction. And I'm really glad you could all be here. Basically, I'm kind of blown away that we were able to bring everybody in here. You know, about 5 years ago when we started working on this code, I had no idea that it would last quite this long, or that it would, grow to be the community that it is. And I'm really happy that we can all come together and sort of learn a little bit about it, and maybe get people excited about developing, but also about doing scientific applications and understanding their data, and hopefully come together and come up with interesting ways of looking at data. So I wanted to briefly put up a slide of thanks. I'm going to go through. I wanted to thank the Flash Center in specific. We've been in contact with Don Lamb, with Carrie Eder, Mila Kuntu, but also organizers John Zuhon and Britton Smith, who were on the organizing committee. And then there was a technical committee of people that reviewed the talks, and we've actually reviewed all of the talks that are going to be given this week, and that's Brian O'Shea, Jeff Awishi, who can't be here today, Stephen Scory, Sam Skillman, and Cameron Hummels. And the National Science Foundation, who have funded us specifically for this workshop to bring a number of you here and to take care of your hotel stays. And on the Stanford end of that, who are administering the NSF grant, Tom Abel, Ziba Madavi, Martha Siegel, and Christine Aguilar. And at the Adler Planetarium, we've had good contact with Mark Subarao. So this week, it turns out that we actually can't cover everything. We debated about just going through and reading the source code verbatim, but we can't do that. And so what we're hoping to have as a big takeaway here is really that YT is designed to ask questions of your data, that you can approach it. You can approach your data with a finite set of tools, and then ask a series of questions, and specifically, to think of it sort of as a library to provide routines from which you can construct pipelines and so on. And so what type of things should you expect this week? What did we put on the talk schedule? Things like narrative descriptions of existing analysis pipelines, examples that you can work through, a lot of labs and homeworks that you could optionally do, some visualizations, some advanced analysis, and hopefully on the final day a little bit of development, sort of digging into the source code. There are a couple things that YT can do, just to give you a sort of a 30,000-foot overview. Starting with handling raw data. So, for instance, if you have a Flash data set, you can examine the individual values in a grid block, or in a block of cells. But you can also hide the data handling. So you could also examine things like spheres, and then have it return those to you. Visualize in 2D and in non-spatial dimensions. Do volume renderings, halos, cosmological analysis, star formation rates, and so on and so forth. A lot of which were contributed by people, by other speakers this week. And so hopefully by the end of this workshop, you'll be able to, for instance, define a derived field, identify halos in a cosmological data set, volume render your data, and we're actually going to be having an evening at the Adler Planetarium where we'll be, displaying volume renderings that you've created this week on the dome. Create publication quality plots, and possibly even contribute back changes to the project. So a good portion of the third day is going to be talking about how one would contribute back if you were so inclined to do so. One of the best ways I think to approach this is to think about an example workflow, and this is actually something that I've done recently, which is to define a new derived field that in a simulation, and in my case, I work on population 3 star formation. And so what I did was I defined a new derived field for the total mass inside a given zone, in both particles and cells. Then I was able to identify topologically connected sets in that. So, looking for the individual cells that are touched by, either that are at some mass threshold or above, and then identify them as separate regions if they are distinct in space. evaluate the mass flux over those clumps to see how they're growing with time, and then to evaluate the gravitational boundedness of those clumps, whether they're bounded or they're unbound gravitationally with their their potential versus their kinetic energy, and then for each one to take a to volume render along the calculated angular momentum vector of that individual clump. And so this is the kind of thing where you assemble pipelines starting at the most basic and then move up to the more complex. This week we actually have 8 presenters lined up. Cameron Hummels, Jeff Oishi, Sam Skillman, Stephen Scory, Britton Smith, me, John Zuhone, and Venkat Vishwanath from Argonne. And so we're optimistic that we'll be able to do some interesting things this week. So we also have a schedule up on the workshop website, and if you have any suggestions about the schedule, we can swap things out, change things up, and whatnot. And everything will be available online, such as the data, the scripts, the videos, and the slides. We are actually versioning all of the talks. So let me pull up the web browser. So for instance, this will be available in a more concise format, but we are providing all of the scripts for both the presentations, the resultant PDFs, and scripts that will be run during the course of the workshop online. All of the talks will be recorded and placed online. And so all these things, we're trying to make sure that everything that's done is readable, and you can go back and take a look at what was done during the week. There's the workshop website is at you've probably gotten this in your emails a couple times, is at yt-project/workshop 2012. On that website, we'll be filling it out with the videos as they come online, the scripts, the slides, and everything. But moving on. So there are a number of sample data sets, and there's at least one USB key floating around the room with these sample data sets. These are the ones that we'll be using for analysis purposes during the week. And so 2 hard drives and a USB key will be floating around. They are about 12 gigs, and you don't necessarily need all of them. If you're going to get only a couple of those, I would recommend ENSO Tiny Cosmology, because it's a tiny cosmological data set. Gas Sloshing, right, is a flash data set from John Zuhone, and Setoff 3D is also another good one for a 3D Setoff blast. But if you want, you can of course grab all of them. No, in fact, only ENSO Tiny Cosmology and ENSO 64 and Isolated Galaxy. So fewer than half of them are ENSO. The rest are all flash data sets. There might also be DD0087 on the USB key, but don't worry about getting that one. Does everybody have YT installed or access to YT? If not, we also have key fobs from Prognesh to log into Nautilus, which is a machine at NICS. So we'll be distributing those a little bit later. And if you're running on Windows, specifically, we recommend using the application Putty, P-U-T-T-Y, to log in. But if you can't install Putty on your Windows machine, you can use an application called Serfish, S-E-R-F-I-S-H, which is it's a Java-based SSH terminal. But Prognesh, when Prognesh distributes the USB keys, he can, or the fobs, the tokens, you can give information about how to log on. Perfect. Cool. For those of you that do have YT installed, there are just a couple things to remember if you want to run it on your laptop. You have to activate it by typing something like source yt-x8664/bin/activate. This is a script actually contributed by Casey Stark, which will set up all your environment variables, make sure that you're using the correct Python installation, and so on. All of these small data sets are probably fine to run on your machine. In fact, all of the data sets should run just fine on any laptop. My laptop is not terribly powerful, and it can do all of the analysis that we've talked about this week on all of the data sets. And if after the end of the week you have buyer's remorse and you decide you don't want to use YT, which would make me very sad, but if you do decide that, it's all self-contained, it's in a single directory, and you can just wipe it out. There's also the command YT paste bin. If you run into problems, it'll just toss a script up onto a paste bin, which you can share with people. To log into Nautilus, you SSH in with your username at login.nautilus.nix.tennessee.edu. That is the correct host name, right? Yeah. When you get your tokens, you'll be able to, they'll come with that information. And you can actually just load the module yt/dev. And so there's Hari Krishnan was unable to attend this week, but he wanted to send his regards, and he also has very kindly updated the YT module on Nautilus. Modules are available on Nautilus and on Kraken, but this week we'll be using Nautilus. And putty at putty.org is an SSH client for Windows that should work. So during this week, there are going to be a couple talks where there are going to be examples given or suggested problems and so on. And the best way I think to code along would be to just create a new workshop directory on your laptop and then symbolically link or copy data into that directory. If you're on Nautilus, I would recommend you symbolically link, but if you're on your local machine, I would say just copy your data into that directory. And then edit any scripts that you write in that directory. Does everybody know how to use like a text editor like VI or Nano or Pico or something? Or okay. There are some other helpful bits. There's a side channel chat in IRC, so we'll be having a side channel where you can chat at irc.freenode.net if you have an IRC client, which would be like ADM or IRSSI. And if you don't, there's a website you can go to with a web client at yt-project.org/irc.html. And so there will be people in there. And the mailing lists are usually very helpful. And for after-hours problems, if you have them this week, if you go home and are motivated to work, if you have run into any questions or problems, just email YT users, which is linked from the YT website, or YT dev, which is also linked from the website. Maybe does everybody try real quick to go to the IRC channel, see if that works out. Okay, and so now there are a couple things on the website. Let me just very briefly show, just because so we have documentation on the website. This is linked from the front page, and it covers a variety of things, most of which we'll also be covering during this week. But on the main website, there's also a number of examples and links to community items, and in fact there's a link to the IRC channel under community as well. Under help, there's information about how to get help, and then documentation, of course. There's documentation. However, during the week it's probably if we chat about this stuff during the day. So let's try our first YT script. And I'm going to slow down a little bit. I have a substantial amount of time left in this talk. So now, for those of you that have already gotten the data, does anybody here already have the data using the download script off the website? Does anyone not have any data whatsoever to look at just now? Okay. And of those, how many of you actually have YT installed? Okay. So there are a couple people that right now we can't do the very first YT script. How should we do the token stuff? I guess Nautilus isn't up until noon. Is that right? Oh, it's up. Okay. How should we handle this? Okay. So then I think for everybody who absolutely needs a Nautilus token, would you mind? I guess there's just 3. Okay. Or 4. So this is the standard methodology that you'll use for running a YT script will simply be to have access to the data, to open up a text editor in your script or your workshop directory, and then we'll cover what to put in that script very shortly. You save it, and then you run it. When you install YT, you get an alias called pi-YT. You could also, of course, just type Python. It's just that this one will be definitely the one that has access to the YT modules. And so, for instance, if I were to run this script here at the top, from yt.mods import star, and we'll cover what all of these things mean. You can load up a data set and then just print out statistics about that data set. So we're gonna walk through exactly what this script means. So at the very top, and this is all Python code. At the very top, this is probably the simplest script that you can do, is we import all of the necessary items. And so what that does is it goes out and it seeks out the Python modules, the dynamic libraries, and so on, and it loads them into the main into memory. So that's essentially the process of starting up YT. The next line says to load a particular data set. Now what it does is it accepts a file name, it goes out, it reads that file, and it attempts to guess if that data set is Enzo, Flash, Nix, Ryan, or art, and so on and so forth. Well, sevart, and so on and so forth. And then the final line is to print out statistics about that data set. So now what you see down here in the bottom half below the horizontal line is this process right here, this loading plugins from my plugins. That's from the startup process of YT, and then it moves on down, and when you load up a data set, it prints out a number of pieces of information. In this case, the current time and simulation units, the domain dimensions, the left edge, the right edge, if it's a cosmological simulation, if so, what its redshift is, what the omega lambda is, what the omega matter is, the Hubble constant, and so on. And then at the bottom, you can see the output of print stats is it shows the refinement level, the number of grids, and the number of cells at that level. So this is just very simple. It's just a diagnostic about what the data set looks like. And then at the bottom, it tells you the units that the smallest cell is in. This actually goes probably to about here. It prints it out for every single spatial unit that it knows. So it'll give you the smallest cell in centimeters, miles, co-moving miles, things like that. Yes. So I wouldn't focus too much right now on trying to run this script. We're going to walk through things a little bit slower in a bit, because I wanted to cover a little bit of jargon, just to make sure that we're all on the same page. So for instance, the term parameter file, this is a non-mesh storing object. So this stores a number of pieces of information about the file. And for codes like Flash, it's actually the same thing as where the mesh is stored. For other codes like boxlib-based codes and Enzo, it's a text file that is sidecar to the fluid quantities that tells you information like when the simulation is in its evolution, is it cosmological, how big is it, and from this you want to be able to do things like inspect the file and decide if you want to start reading in the mesh information in order to load it up. The process of loading the mesh can be a bit more expensive than just scanning the file quickly. So for instance, if you're doing something like going through a series and you only want to evaluate and study those parameter files after some given redshift, if you don't know that a priori, you can scan through it without loading any fluid quantities from disk, and then evaluate it at only those that are necessary. And then the hierarchy is sort of a holdover from the Enzo days, and will likely change at some point. But the usage, but this is sort of the mesh information. So when you load up the hierarchy, which hangs off the parameter file, it goes out, it understands the block structure or the grid structure, and then it also instantiates a number of Python objects, all of which are able to access data off disk. So this is a much more heavyweight object, and for hierarchies that have in the hundreds of thousands to millions of grid patches, this can take it can take up to about a minute to load, and you don't want to necessarily do that, which is why it's conceptually distinct from the parameter file object. All of the subsequent geometric selections, so selecting spheres, selecting rectangular prisms, selecting cylinders, and so on, all are interfaced through the mesh or hierarchy object. So a grid patch is a rectilinear collection of cells. Flash users might know this as a block. So the idea being that this is some collection of cells. And for octree codes like ROMSES, this is actually applied after the fact YT in order to because array operations are a little bit faster than individual operations. So we create grid patches later on. But these are essentially a contiguous block of fluid data. They can contain particles, they have extent, and they have a number of dimensions. For the most part, unless you're actually manually inspecting your data, these are not necessary to deal with. But you know, it's probably a good idea to understand what YT is doing in the background. So profile objects are essentially one or two-dimensional histograms. These can be things like radial profiles or density PDFs. And these can also be weighted or unweighted, which means whether or not you take an average or just sum inside bins. So these are essentially two-dimensional or one-dimensional or even three-dimensional histograms, which may or may not be averaged rather than accumulated. We're going to go into depth on a lot of these. A slice is an infinitesimally thin variable resolution object. One thing about two-dimensional objects in YT is that they all actually are variable resolution unless you explicitly ask for fixed resolution. So when you take a projection through the domain, what it does is it takes a line integral at every single finest resolution point along each line integral. So you might have coarse points, you might have fine points, depending on how that reduction operation along the axis proceeds. And then a slice is exactly the same. So if you slice through the center of the data set, some cells will be of different width than others. A cutting plane is also, it's an off-axis slice, which also is a variable resolution. And a projection specifically returns, x, y, dx, dy, and value at every single point along a face of the simulation volume. This can either be just a straight line integral or an averaged line integral, where you multiply by the weight before you sum. So with all of these variable resolution objects, the process of actually making an image is referred to as pixelization. So this is generating something like an object called the fixed resolution buffer. So the idea being that if you want to project through the entire domain, you only have to do that operation once, and then you end up with this variable resolution object, which you can then pixelize into essentially infinite objects. We're going to show you a tool called the map server in a little bit, where what you can do is you can take a single projection through the entire domain. It constructs this variable resolution resultant object of data, which contains the x, y, the dx, the dy, and the value information at every single point. And then what you can do is you can actually interface with this in a Google Maps-like interface. And you can zoom in on a cluster or on a galaxy, and you can zoom out, you can go somewhere else. And it doesn't have to do, it essentially does nothing during that operation. What it does is it just pixelizes a variable resolution object into a fixed resolution buffer every time you ask for a new map tile. And we'll show that a little later. So typically volume renderings in visualization refer to something typically volume renderings are used to refer explicitly to something that is that's designed for visualization. But with the volume rendering engine that Cameron and Sam are going to describe this week, visualization is actually a side effect. It's any traversal of the grids that is along some axis. So this could be, for instance, calculating column density outward from a central point in a simulated galaxy. It could be, visualizing iso contours. It could be taking the weighted average in order to calculate the Toomre Q inside an off-axis disk, things like that. It actually integrates the radiative transfer equation, and so this can be back-purposed for things like volume rendering or for visualization, but it can also be used to take weighted averages as well. And just a couple helpful hints, and then I will terminate and turn the mic over to someone perhaps more eloquent. Units in YT are, whenever possible, done in CGS. We'll show you how to get information explicitly about units and fields a little bit later. Length is typically available in code units, but you can also use a tuple of the form like 2 megaparsecs in many cases. So if you ask for a sphere, you can either specify the radius in code units or you can ask for it in 2, MPC. And that's basically it. That wraps up my introduction. Again, thank you very much for hosting us this week, and I'm optimistic that there will be a lot of fun stuff going on. So I guess we should probably distribute some tokens, or that's all